20 May 2023. Saturday afternoon. Pleasant. Scattered clouds. Canada's on fire. Smoke isn't here yet. Global warming and all. Record highs. So continuing to read about these differential equations, last time there was a lot of reading from Emery Lakatos, and it got into a lot of the definitions about the convergence in the series and these kinds of things that were of the miseries of induction that Abel referred to as Euler's misery of induction and Abel's misery of induction. And we got into the discussion of the definitions of things, and that the very definitions involves that there are quite a few different theories that result that their objects are elementary in mathematics, and by elementary it means they establish relation and the basis of relation for each other. So there's number theory and for arithmetic, and they're not necessarily the same thing, vis-a-vis that the point at infinity is usually ascribed to live in number theory or geometry, projective geometry. And either, but it's something that is an object of mathematics, isn't necessarily part of arithmetic, which people usually have as Archimedean in the Archimedean field, which could as well be described as the coming together of several models of almost numbers, ordinals, which only express an order, they don't express any sense of magnitude with respect to each other, but as objects of the increment or what, then make for the objects of addition besides, and that being just a higher order operation, then objects of multiplication besides, and those being the same ones, and this being a higher order operation, reflect that there's these three replete definitions of an operator and these additive numbers. And then it's similarly with division with respect to, one might aver that there's a complement to increment, like decrement, and whether that lives as an inverse to addition or that it lives as a sort of lower order division in arithmetic, has that in the sense that addition and division are these reflective sort of actions, one representing an aggregation or summing or putting together things, and the other one representing a cutting or a taking away or a splitting of things. So for arithmetic and algebra, and then that algebra is in terms of the quantities, and where it's established that when we have collections of quantities, then according to, usually it's treated as according to their membership in groups, and that there's groups about the divisor bar, quite abstractly in terms of numerical quantities, so that these are objects of arithmetic, the numbers, and then that they're objects of algebra, the symbolic values for elements of said domain. Then there's in many of these developments and their derivations where it results that quantities are bound together, and they either can or can't be put together, taken apart, and canceled together and canceled apart with other similar terms in like variables and dimensions and inequality. And it gets these things like here, there's the idea of this identity dimension, or when y equals x in the positive numbers is considered the dimension, say, and instead of just like the x-axis or the y-axis. That then there's also where in this algebra, in these quantities, that there's these symmetries established, like, hey, well, dx equals dy. Well, really, the idea is that there's a frame for this, compared to that something like, well, what's the x squared's root is plus minus x. Oh, it's plus x or minus x. Oh, really? That these are the kinds of things that get into this restriction and expansion and comprehension about their duals, about when they're alternatives, when there's the bivector, when there's two heads to the arrow, as it were. These are the kinds of things that get into these matters of fuller definition for arithmetic and algebra. And then we have analysis, And so analysis is basically anything to do with continuous real valued formulae. And the summation of infinitesimal areas is called the integral calculus. It's analysis. Or computing the derivative or differential or the gradient analysis. And so it's kind of similar when we have different objects of the realm of analysis. Well, what goes into making an analysis? Well, we have numbers, and then the algebra is pretty much set up to make it accessible to the rest of algebra and later to the operator calculus above algebra. That the operator calculus is like, this is what's left we can deal with in these quantities. And so that's just kind of the working theory. And then this real analysis has a thing going on, needs a continuous domains, and it needs the intermediate value theorem, and then these fundamental theorems of calculus. And then after the definition of the limit, then it's possible to work up from those the fundamental theorem of the derivative or differential, which is where you kind of take the function f of x and plus f of x plus delta h, and just let h go over delta h or over h and let that go to 0 to show that reflects that if that exists, then it can be so represented as how the various rules for computing for usual elementary functions and power series and polynomials and the trigonometric functions and their products, especially the chain rule and the product rule, enable one to compute the functions that are the derivatives of functions and arrive at then how to evaluate those. Similarly, for the fundamental theorem of the integral calculus, it's so as when it goes to infinity, all those terms that they're added up, that their widths go to 0. This is the usual Riemann integration. And there is some discussion here about how that is. And then for an example, just in this toy application of the identity dimension, saying, oh, here's another kind of integration. You can, as long as you have a function and it's everything under a curve that happens to be symmetric on either side of the identity dimension and the rest of the quadrant, then it can be computed by computing half of that and doubling it. These are kinds of interesting things in a sense, or examples of a derivation that's simpler than when the usual derivations end up being more complicated. It's like, well, we'll take the numbers from the positive numbers to the positive and negative numbers in one and then both dimensions. Oh, well, then we'll also figure out how to define a new set of coordinates about these complex numbers by having an imaginary component and a real component. And this is already after we already have just numbers with just an integer part and a non-integer part. That we have a real component and an imaginary component, or these kinds of things, or like a part of a real number that's approximation, the rest is the error term. These are similar kinds of ways to define how the numbers are and what remain and how their product rules work up in these tensors, or the tensorial products, or the operator calculus of sort, which for most people is familiar as algebra. Algebra is an operator system. The operations of arithmetic are ... That's the working theory. So getting into this leads to a lot of different things. And so I've been just reading the old school text. And so the old school text is the 1950s, 1960s, early 60s text. And so it's a little bit different than the modern text, the 80, 90, 2000 texts. And basically the emphasis is on the plane curves, or at least so far in this book, the emphasis is on plane curves and their integral equations instead of the differential equations and their solutions. Where these differential equations are defined in terms of differentials, but the integral equations that get built up are defined in terms of basically making it like so pre-derivatives, the integral equations. So it's quite different approaches. The milieu, the objects, are two different theories. And then where they come together is that a lot of their things come together, some of them don't. but they're each good for what they are, and then there's some notion that the plane curves and integral equations seem a little bit more suited to usual milieu of the pencil and paper apparatus, and as well for the usual milieu of more familiar 2 and 3 dimensions of space. Whereas the differential equations, given that there's treating the differential equations and finding solutions with regards to their order and their powers and their rank and this kind of stuff, makes it so that while it's then suitable for those, then it's a little bit easier to extend it in some senses, and it's usually maybe a little bit easier to also to get it as tractable as possible, then throw it at a computer and expect the computer to provide computations of it and solve it. And so there's lots of things that go on to that, but it's all eventually, whether it's on paper or on the computer, it's still the same amount of pencil pushing to arrive at the solution, the same amount of abacus counting, or it would take the same amount of beach in the sand with a stick to draw out all the carried terms to compute all these different things. So it's still better to keep it symbolic in the algebraic about the variables as much as possible, because that's more concise. If anything, that's still easier to compute by a person is still better, and not just because we don't want to be slaves to our bots, and nor unfamiliar with where our derivations come from. It's like know your food, know where your food comes from, and this kind of thing. So we've been reading about D'Alembert's and the Lagrange's equation, and log phi p equals the integral of dp over gp minus p prime, or excuse me, gp minus p. And that gets into here for this integral equation that says for this plane curves x equals y, and then next 1 over x is about how to arrive at something like the integral of log is x times log x minus 1. Well, that's remarkable. Well, what's the integral of 1 over x? It's log x. What's the integral of log x? It's x times log x minus 1. Oh, okay. Well, how about, x? Well, it's half x squared, and then it's, 1/3 x cubed, and ... That makes for the nice power rule. But how it comes up from the negative powers, because as it goes down, it goes x cubed, x squared, x, and a constant. And then figuring out how it goes from 1 over x up to log x is really remarkable. Because otherwise you might try and think of something that comes up to a constant. And this gets into the whole kind of thing is like, well, all of physics and motion is basically based upon rest, and then there's velocity is dv dt, dp dt, displacement over time, and then acceleration is that in time, and the higher orders acceleration of that in time. But then there's some kind of question of how the growth adds up, so that well, what about coming to rest? How about if you integrate it is you compute the difference as when it comes to a stop at the stopping distance. So I guess that reflects there's this complementary notion of stopping distance as there is for 0 to 60 in time is this notion of stopping distance. And so when we're used to computing our derivatives and differentials in the powers, and they go up, and come down from the positive powers, it's so from a constant. And when they go up and come down from the negative powers, it's as up to the logarithm. And then I'll be interested to be looking into what are the higher order integrals of 1 over x. And what with regards to then how it works out, that eventually goes to some power, where x log x minus 1, it goes to x squared, or where log x minus 1 is approximately equal to x. So that would be log x minus 1 equals x is kind of between 1 and 2 there somewhere, I suppose, as an example of these kinds of things. So in looking at the identity dimension and being able to find that it's in the middle of all these things like the linear fractional equation, and that it ends up being an important spot in this singularity analysis, and this place of it's undefined in the middle. It's the middle of nowhere for these either sides of about the ovals and ellipses from the origin this way, is for finding where such then simple operations and otherwise numbers in these trivial and vacuous cases come out of these otherwise these totally simple cases that are basically about exactly one-to-one functions from the rank or the order to a number, and that they maintain just like an addition formula and summing to powers. You can just sum the powers and call that the product of the powers, an addition formula. And this is kind of an index notation or an index assignment. That here, when there's not those, and it comes up to that, it comes from x to the negative 1, which is derivative gets down to x to the negative 2, and it goes down. But when it comes up to that, it doesn't go to a constant, it goes to ln x. So it's really remarkable to figure out then how stopping distance and 0 to 60 are these similar types of things, one in time and one in distance, about how for these differential equations and one or the other, and that usually everything's parameterized by time, that is still a function in time, and the diminishing rate of stopping distance, how it adds up to make it so that then there'll be this complementary dual as about what's necessary to add up the other side in the complementary dual for systems of motion, which nobody's ever really, that I recall ever told me or gotten into this kind of development, except for the fact that it's just an example that it really has an accessible metaphor, stopping distance and 0 to 60, that adds up for why those are symmetrical, while at the same time defined in different quantities and units, and as to why then the solutions of either kind of admit a very particular neat linear solution, but what they both demand is solutions in terms of each other, how they can be so perfect and line up. So I that's kind of just a distraction because I found it interesting, and otherwise my facility with the D'Alembert and Lagrange equations here is not particularly great, because all the way along in this Clairaut equation and these linear fractional equation, especially about the center and the limiting point of the ellipses, about the principal lines and principal directions, that I'm really finding a common thread through all the development of the linear analysis about this identity equation, about this kind of in the middle, and it has that, and that's one reason why it has a lot going on, is because anything that's differential is basically framed in two quantities, dx dy. The f prime, or Newton's notation for the fluent of the flunction, is always with respect to the range. And so this fx equals y that has a constant derivative or differential, it's 1, is as well parameterized by those two together, and it's different from there being a constant that's 0, which is just the x-axis by itself, that it really does speak to that then this identity dimension is pretty central in the differential analysis. And I suppose then it would be so when you have like x equals y equals z, which reduces to this, x equals y. And as with regards, then that would go around for stuff like the Christoffel symbol, CIJKL, and lots of different milieu where these are not so much imaginary numbers as sorts of diagonals. They're diagonals in a sense. In particular, general integral in equations of higher degree about a singular solution, the D'Alembert equation, since dp dx, and in this writing it's p is dy dx already, and there's so dp dx is dy dx squared, as it were, or the second derivative of y with respect to x, in terms of that y is a function in x here. So there's the reading of the D'Alembert, and phi p is an integrating factor, and the general integral is gp minus p, where g was defined as that it does not cancel out with p, and we cannot have dp dx equals 0 identically. Although here it's 1 or 0, because dy dx equals dx dy. Differentiating that gp minus p quantity phi p x equals c minus the integral of f prime p, and so the integral of f prime p is that is constant minus phi p dp. And so here, as I'm reading out D'Alembert's, I'd go back to just the general and the real value and read on here. Thus, x is expressed in terms of p and the arbitrary constant c. So these are for all the other equations, and then basically this x equals y, which is undefined in the middle. By eliminating x between the D'Alembert equation and differentiating with respect to x, y may be similarly expressed, and thus the general integral may be obtained in terms of p, regarded as a parameter. It is only exceptionally that the parameter can be eliminated and the general integral obtained as a single equation between x, y, and c. Usually, that is taken together with the equation itself must be considered to furnish the general integral. Example, y equals x plus p squared plus 2/3 p cubed. This is of the above form, differentiating with respect to x, p equals 1 plus 2p minus 2p squared quantity times dp over dx, or p minus 1 of 2p dp over dx quantity plus 1 equals 0. The alternatives are either, and this was read into before the previous talk, where the previous talk was much about convergence and Cauchy and Abel and Then the talk before that was reading this section with respect to the co-semi-dimensional and this D'Alembert, and which of these alternatives show up for this function, p equals 1 and 2p dp plus dx equals 0. Substituting p equals 1 in the original equation, and here that's what it is already, so it's trivial in a sense, we find that y equals x plus 1/3. So that's not the solution. This solution will be set aside for a moment. From the second alternative, we obtain p squared plus x equals c, and so p squared would be 1 plus x plus 1 equals c. Introducing y from the original equation, we may express this general integral as x equals c minus p squared, y equals c minus 2/3 p cubed. So this will be interesting to see what those will be in terms of then leaving it formulaic as about that it's possible to assign a constant, and not just a usual constant in terms of that this constant will be added to the solution in this plane, in this axis, but this constant will be able to be written as a function of a curve that crosses this identity dimension from the otherwise the semi-dimensional axes. Because that's the placeholder that makes for it, that anything that is on that would still make it so that its roots add up and make it a thing. In this case, p can be eliminated to give the general integral, the form 9c minus y squared equals 4c minus x cubed. So this reflects, in powers of 2 and 3, then this that the constant that the curve would be as of this negative y squared and negative x squared is coming from a constant, so it comes down and intersects this xy on the identity dimension, or x equals y. And as with regards to what constant will hold up for, so that these parabolas and cubic equations make it so that multiplying out c minus x squared also has terms in the second and first order, or with respect to actually just breaking that apart arithmetically, in a sense, so that c minus x cubed does not have its intermediate terms. This is an example of a kind of projection. And what it intends to entail is that it's possible to then think of that negative x cubed is kind of what results from c minus x cubed, c minus x quantity cubed, in terms of that these intermediate terms will be in terms of c and as in multiplying c minus x and getting c squared minus 2cx plus x squared, and multiplying that by c minus x, and that's getting that expansion of terms, and that there's a term in order c cubed, and there's a term in order x squared c, and a term in order c x squared, and a term in order x cubed, that it's only x cubed, and everything else is kind of left off as a constant. Here then the idea would be to figure out how to make it so that, and again I went right back to this E-day fix, that it's, you got to be able to I want to be able to compute it off the this identity dimension which I'm developing, which is the middle of these other things, to make it so that these results are building up. So the first E-day fix is a spiral space filling curve, and the second now is that addition and division are separated, and this third one now is this identity dimension. Then this fourth one now is this stopping distance, or the integrals and derivatives which comes to constants, in terms of time and rest, and velocity, and coming to rest and coming to speed. So here, and then it's again framed in terms of this identity dimension. The abscissae are given by 3x quantity plus 1, that quantity squared, or a 9x squared, 9x squared plus 6x plus 1, plus 4x cubed equals 0. So here he's kind of, I've written out, that's kind of what I'm interested in, is this 4x cubed, and this abscissae is the ordinate, or whatever, that's the intercept, i.e., and so maybe I've kind of subconsciously read forward and applied it to that, but that's what I'm trying to compute here, i.e. 4x cubed plus 9x squared plus 6x plus 1 equals 0, or x plus 1 quantity squared times the quantity 4x plus 1 equals 0. Thus the line touches the particular curve c equals 0 at a point of abscissa -1, since the other integral curves of the family are derived from this particular one by translation parallel to this line y equals x. See, here he said it. He said y equals x. Since the other integral curves of the family are derived from this particular one by translation parallel to the line y equals x, which leaves the line y equals x plus 1/3 invariant, every curve of the family touches the line y equals x plus 1/3, which is their envelope. So here you started to find envelope, because this notion of the envelope really hadn't been very well defined yet in terms of these plane curves. And so it seems I'm kind of reading in this higher order development, there's this missing chapter. I almost feel like I'm writing a story about this enigmatic x equals y in the identity dimension. And yes, I am making this up as I go along. further generalization of the D'Alembert. The integration of any differential equation that can be solved algebraically for y in terms of x and p, thus y equals fxp, may be attempted by the same device of differentiating with respect to x. This gives p equals partial of df dx plus df dp dp dx, the partial of df with respect to dp of dp dx. And here it's kind of hard to figure out how to read that as, instead of saying delta, I imagine here it's fair to say that anytime I say delta, it means Greek scripty little d for delta for the partial differentiation, whereas d for the differential in the Latin d just means regular differentiation, or the raw differential, as it were. And partial differentiation can almost be read as more fully differentiation, because it treats the other side constant. This gives p equals delta f over delta x plus delta f over delta p dp dx, which is an equation of the first degree in dp dx. Its general integral, p equals phi x comma c, or x equals psi p comma c, as the case may be, associated with the y equals f of x comma p, furnishes a parametric general integral of the latter, x equals psi p comma c. On the other hand, if p minus d delta f delta x and delta f delta p have a common factor involving x and p, 21.2 will be satisfied by equating that factor to 0. An equation which may furnish a singular integral. So here, if p is dy dx and y equals f of dy dx is just y equals x plus 0p, in a sense that, and then does p equals df dx? Yes, that's 1 plus, yeah, it does, which is an equation of first degree in dp dx. Its general integral, and equations. And here I'm interested in then, well, what happens is this is trivial, it's vacuous, but it stood up that this stuff is sitting above it and would fall into it. An equation soluble for x, i.e. one that can be expressed in the form x equals f y comma p, may be attacked in a similar manner by differentiation with respect to y. So attack means as a problem or a challenge or finding a solution. It just means to deconstruct something and to result that there's something sensible, fungible, and tractable that reaches a goal. With respect to, for example, studying a game like chess, which is a competitive game, and there are openings and mid games and end games, and there are combinations, and there are lines. There are various ways to describe games. There's a descriptive apparatus. There's a culture of it. There's historical names for lots of these things and features of it. There's various common strategies and tactics. There are certain particular known closed forms. As a game theory, in a competitive game theory, there's some only rational behavior. Nobody throws games in chess, abstractly. Compared to that, failure, as it were, in an attack can be like, how can we lose fastest? Because all I really care about is time. Anyways, that's not an unusual thing in mathematics sometimes, when it's like, I don't want to know how it's solved. I just want the numbers. Some people have this approach, and that's their tactic, and there are others. Differentiation with respect to y. Example: y equals x over x plus 1p plus x plus 1 times quantity e to the x over p. So this is his example of a function y that's defined by x over x plus 1. And so here, if that's going to be this kind of function, for x over x plus 1 times p to be equals y, this x equals x over x plus 1 p, and so 1 equals 1 over x plus 1 p. As an idea how to separate that into two terms, so that y equals that times x plus 1 e to the x, then having that multiplying that over p. The idea is I'm replacing x or y with x, and then solving for x, and so putting it back in the example and see what falls out. But for now, I'll just leave it alone. Differentiating with respect to x, p equals p over x plus 1 squared plus x plus 2 e to the x over p. So far, it's pretty clear. Plus quantity x over x plus 1 minus x plus 1 e to the x over p squared dp dx, i.e. quantity x over x plus 1 minus quantity x plus 1 quantity e to the x minus, or excuse me, over p squared, and quantity dp over dx minus quantity x plus 2 over x minus 1 times p equals 0. I used to have pretty good facility with solving integrals and derivatives. I have some pretty good books, like the handbook tables of integrals, series, and products, and it has a lot of different. It's pretty amazing when you get into it. It's hundreds and hundreds of pages of integrals and series and products for various formulas, and so I was pretty good with finding a derivative, being various rules and the application of derivations and substitution of variables and the chain rule especially, and the product rules. The second factor gives a differential equation whose general integral is p equals c times quantity x plus 1 e to the x. So, currently the only thing I really have in reference to that is about the integral of ln x, which says like x times the quantity ln x minus 1, and e to the ln x equals x, and ln e to the x equals x. That it's they're reciprocals and inverses in terms of composition of functions. But here, substituting for p in the original, we have its general integral, y equals cx e to the x plus 1 over c. And so here we have how it's building out that there's c is in its power and its order and its term, and c can be a large constant plus 1 over c is these together. When we see things like e to coefficient e to the x plus coefficient e to the negative x, that's a pretty big deal, and it gets in all these Fourier series. The first factor gives p squared equals x plus 1 quantity squared e to the x over x. So there's some ideas sometimes when there's constants that they have geometric interpretations, and so they'll establish something like bounds. And so when they make, for example, a square, and they make it so it's like, okay, it's a 2 by 2 square, and this constant is 2 on the y-axis and 2 on the x-axis, and there's any particular curve that connects them. Whether or not it's symmetrical about x equals y would be a great thing if it would make a lot more information. But here, though, just think of that as a constant, and then think of that in terms of a parameter, is that now according to the shape and the scaling of this curve, according to that constant, if we have a function that's the variable instead of the constant, is this idea about how to exchange parameters with regards to kind of a partial differentiation. You can also have this sort of constant parameterization. And what it does is it makes a way to just plug in values and get different ones, and then according to the rules that it's done so, and what rules are observed and how it carries forward, it's possible to make inferences about what results as systems of equations that it so represents. So it's not so much saying much, except that when it gets to these forms, then it looks like, okay, well now we have these forms and constants that look like these forms and variables and powers. Well then, where it's possible to so parameterize those by their constants and that the constants are related, as that they essentially admit being the same variable, is for those. That besides, the differentiation and integration as these reciprocals or inverses in terms of their composition together, that the integral of a derivative is the integral, or that one of the derivatives of an integral is the derivative, or vice versa. With regards to the principal branches, the main branches of these things, that root x squared equals x, that negative a equals a, or here that these substitution of variables and substitution to constants can make a symmetry. These are interesting things. The first factor gives p squared times the quantity, or p squared equals the quantity x plus 1 squared e to the x over x. So if that were x equals y, then it would be 1 equals x squared plus 2x plus 1 times the quantity e to the x over x. But it's not here. But on the one hand, integration of this gives y equals 2 root x e to the x plus constant. On the other, substitution in the original equation gives y squared equals 4x e to the x. This is therefore a singular solution that may be verified to represent the envelope of the integral curves. So again, I need to figure out what an envelope is here in this world, because the y squared equals 4x e to the x is only so when this, if x equals y, that, the x squared equals 4x e to the x, or that 1 equals 4 e to the x over x. Or 0 equals x times the quantity 4 e to the x minus x. See, this is an interesting way, because then it allows one to consider that as a particular thing that's otherwise a given, that they're so parameterized together, making it square, it's kind of a thing. This is therefore a singular solution. It may be verified to represent the envelope of the integral curves. The envelope. 22. Equations with one variable missing. If an equation of either of the forms f x comma p equals 0 or g y comma p equals 0 is soluble for p, thus p equals f of x or p equals g of y, integration by quadratures is immediate. On the other hand, we may consider cases in which solution for p is impracticable, but solution for x or y is possible. If, for instance, we have x equals phi of p or y equals psi of p, and here that p is dy over dx, so it's not a function of dy over dx, except where it's equal to 1. The second variable, y or x, is expressible in terms of p by quadratures. Thus, if x equals 5p, we have y minus c equals integral of p dx, which is taken from 0 to x, that's 0, equals integral of p phi prime p dp, and where phi equals x. Oh, yeah, that's the condition. Or alternatively, y minus c equals integral of p dx equals px minus the integral of x dp which is 0, also, equals px minus integral from phi dp dp, so that here the integral of phi of p dp equals px. And if y equals psi of p, we have x minus c equals integral of dy over p equals integral of psi prime p dp over p, or x minus c equals the integral of dy over p, which is 1/2 x squared, I suppose, because it's kind of tough here, because when he has p as dy over dx, whether or not it's accessible in algebraic in those terms. But again, I'm just reading it kind of here in just a manner of getting some introduction to these equations of higher degree, these D'Alemberts. Another method is to replace the given differential equation by its equivalent in terms of parameter t. So from reading before, x minus c equals integral of dy over p equals y over p, which is x or y, plus the integral of y dp over p squared, which is 0, equals y over p, which is x or y, plus the integral of psi p dp over p squared. And so yeah, that does add back up that it's that dy over integral dy over p would be like under the parabola, under that. So on the one hand, we have that from the one side it says of the differential, because p is dy over dx. So in terms of x, it looks like under the diagonal. In terms of y, it looks like under the parabola, or the 1/2 x squared. So it's kind of interesting in that sense, about either side of the quadrature, and what I would call a quadrature wall, because when you think about gravitational singularity or something like that, it has kind of what's called the event horizon, kind of the wall of the black hole. The cube wall is that from the inside, things act like linear, but on the outside, things act like inverse cube. It's kind of like a cube wall. But at that wall, this should be the same. So here it's in this identity dimension. It's some notion of a quadrature wall. Another method is to replace the given differential equation by its equivalent in terms of a parameter t. Thus let g of y comma p equals 0 be equivalent to y equals phi t, p equals psi t. Then x minus c equals the integral of dy over p equals phi prime t dt over psi t, which taken with y equals phi t gives a parametric representation of the general integral. Example, x squared plus equals p squared a squared minus x squared. Solving for x equals ap over the quantity root 1 plus p squared. So here this x equals p squared, a squared minus x squared. Would just be that a squared minus 2x equals 1, which is similar, and then has those solutions of in squares and in the linear, because the x terms vanish and p squared is 1. Yeah, and when I say the x terms vanish, it's just that they're on either side of the equal sign, so they can be algebraically canceled. Solving for x equals ap over root 21 plus p squared, i.e. dx equals adp over 21 plus p squared to the 3 halves. Hence, y minus c equals integral p dx equals a times integral p dp over the quantity 1 plus p squared quantity times to the 3 halves equals negative a over root quantity 1 plus p squared. In this case, p may be eliminated, giving the general integral x squared plus y minus c quantity squared equals a squared. And so that's x squared plus x squared minus 2xy, or 2xc plus c squared equals a squared, or a squared minus c squared equals x squared plus equals 2x squared plus 2xy, 2x, or x squared plus x equals a squared minus c squared over 2. So then that's this notion of this quad wall or whatever, that you got this x squared plus x equals a squared minus c squared over 2. That becomes kind of an interesting way to look at it when you think of defining the usual dy dx as this function, this derivative, p, and then with regards to either way, when it's interpreted for solutions about this identity dimension bit, that there's these kinds of things that make for this kind of interesting stuff up about it. Solving for p, example 3. Then he says this is equivalent to y equals a sine t, p equals a cosine t, dy equals a cosine t dt. Hence dx equals dy over p equals dt, i.e. x minus c equals t. See here, it's almost similar. He's made a similar sort of assignment about how it works out, that this way that be the substitution in terms of these functions, and getting into the operators is about it. You know, that this would have a formal, perhaps more formal way to write it in terms of the operator calculus. And then to represent it in these trigonometric functions, and the derivative in also function in cosine and dt. The general integral is therefore y equals a sine x over c. So then I'd be curious to see how that could extend to make it so for this quad wall that there's something like a sine x over c when there's this x squared plus x equals a squared minus c squared quantity over 2. Section 23, homogeneous equations. Just as a homogeneous equation of the first degree can be reduced to integrable form by the substitution y equals vx, or here that is as by y v equals 1. This is as if after the linear fractional bit, though it's kind of in the middle of nowhere, so it's outside the definition in a sense. Y equals vx, so also can an equation of the form fxyp equals 0, where f is homogeneous with respect to x and y. For if the degree of homogeneity is m, f of x comma vx comma p equals x to the m, f1 comma v comma p equals x to the m g of v of p, say, and the equation becomes g of v comma p equals 0. And here, for x equals y, that's also one that g of p equals 0. And so it kind of has the previous solution. If it can be solved for p, say p equals phi of v, well, yeah, because p equals 1, we have v, which is 1, plus x dv dx, or equals phi of v, and that's p, yeah, because that's dy over dx, and proceed as in section 4. On the other hand, if it is soluble for v, say v equals psi of p, and it's 1, yeah, and they're the same actually, we write y equals vx equals x psi of p, that psi of p is p, equals 1. When it's differentiated with respect to x, so this is dy dx cubed, or here he writes p equals psi of p plus x psi prime p dp dx, i.e. dx over x equals psi prime p dp over quantity p minus psi prime. And integrating, we obtain x and thence y in terms of the parameter p. So dx over x equals because so psi p equals 1 and equals p. So p equals 1 plus x psi prime p, which is a constant, and so it's 0. So yeah, 1 equals 1. And integrating dot dot dot. Well, I guess that's kind of where I got getting up to today. And what I kind of need to review, and I'd like to understand a couple things. One is the envelope, because there's a very telling notion about the envelope and about y equals x and this whole identity dimension bit. So why is the identity dimension bit a thing? Because, because any differential is defined in terms of two quantities, dy, dx. There is no raw differential, really. It's only really well defined, usually, for the quadrature in terms of two variables. And so this y equals x is going to be a central thing. And why is that this envelope is about these curves, is about the principal lines and the ideal lines, is about this diagonal right through the first quadrant, that it's a central thing. And then another one was about the power rule, and that when you take the C empty function, if you take the derivative infinitely many times, you get a constant and it's 0. But if you have a C empty function that's and you take, if you have a function that's a negative power of a number, and you take its integral infinitely many times, then you'll eventually get up to that it's not in powers anymore, that it gets something to ln and x to ln x minus 1. I'm going to be interested in finding all the higher orders integrals of the negative powers. Because what I'm interested to find then is for this 0 to 60, aka stopping distance, that one's in terms of time and the other one's in terms of space, that they both reflect about the same thing in terms of one's coming up and the other one's coming down, in terms of they're both integrating like the changes in the velocity and vis-a-vis the change in displacement. Because I figured that would be very useful to apply that to figure out what's in the middle of that nowhere that makes it possible to add those up. And the other thing then is that there's been more of the E-day fix on the the spiral space filling curve is a long to go E-day fix. That's fundamental in definition of a continuum, line continuity, field continuity, signal continuity, dot dot dot. But it's present in very many places, and it's its own antiderivative. So it's a singularity for singularity theory. So it's very central, and it's a thing. And then this identity dimension is quite a thing. And then here what would be something along the lines of derivative stopping or something like that. Derivative stopping. That's kind of what I'll be trying to figure out, and first by refreshing my familiarity with the usual known forms for same, because if the integral exists, then that should be principal. And I'm not so sure what to figure how there would be other ones, whereas the derivatives could be like so, and this kind of thing. And so this will be of how I'll carry on then from here. So that for today, that's the talk about differential equations. And what I'll consider then is get more into the Fourier analysis. I've been studying some things in radar and the ambiguity function, which is kind of like the error function, and the near field and far field, and how that would reflect on these nonlinear electromechanical effects and applications, and about how sometimes some of the aspects of the field are infinite or infinitesimal, because those are real, and whether or not mathematics provides them, engineering needs them. and they're modeled by non-standard functions like the Dirac delta as ideal. And they show up in these kinds of things. And so on.
Well, have a great day. Goodbye.